Good afternoon to all. I, Rupaldeep Gill, Department of Computer Science and Engineering, welcome you to second session of Atal Academy sponsored online FDP on blockchain technology and its applications. This session on the topic of cryptographic tools for blockchain. This session will be taken by Dr. Professor Shekhar Verma. Welcome you, sir. He is professor in IIIT Allahabad. Over to you, sir. Shekhar, sir, can we start?
Some wonderful lectures on basics of cryptography and blockchain, applications of blockchain, listening to different aspects of blockchain. So I'm talking about what are the cryptographical tools or what is the cryptography on blockchain which enables blockchain to function. So after having wonderful lectures from the industry, let's switch over to something in academia, something more fundamental, something which is not so interesting as the applications are. So I'm not going to talk about any application. I'm going to talk about just cryptography, and even then, not really about cryptography. So let's see what is in store for us in the next 1.5 hours. And let's start. So I'm Professor Shekhar Verma. I work as a professor in Department of Information Technology at IIIT Allahabad. So the first thing that I would say is that don't be very so hopeful. And I'll not really be talking about too much about cryptography. I'll just touch, as I said, the tip of the iceberg. I'll be talking about blockchain. I'll not be talking about Bitcoins, except in the introduction session. And then basically we'll see how cryptography is really. So don't be very helpful. Really so hopeful about blockchain. So here are two ladies and they wish to exchange cash. So they have cash, they have rupees, and they transact in rupees, which is cash. What is important here is that they have to be in physical proximity of each other to be able to share or able to exchange cash. Now, I don't want this physical proximity for exchanging money or exchanging cash. So what do? I take the help of a bank. So for example, goes physically to the bank. Near to impossible to know from the cash itself, whether has come or the money is from one person or the other person. Now, the digital asset exchange. In digital asset exchange, when we want to pay, what do we pay? We have an app. For example, we have Paytm, we have Google Pay, we have Beam, or we have PayPal, for example. So both of us have the app installed at our ends. And we pay through the bank, we pay from one person to the other person. So this is the digital asset or digital money. What is the problem here? The problem here is that the bank, that the persons who are getting the service and the persons who are giving the service, suppose I buy some from the hotel person knows who I am. So the problem is that my privacy is preserved. First problem. And the bank also knows how much I've spent. So what is happening here is that I have an app which is breaching my privacy. So anybody who's offering me service, the hotel person or the vegetable person or anybody from whom I take my service or item knows my identity. Whereas in the case of cash, I go to the hotel, eat, give money and come back, and the hotel person never knows who I am. My privacy is preserved. The second problem here is that for my money, I need and most importantly, from our point of view, the bank is to be trusted. The bank is a trusted central entity. So now what do I want? I want the digital currency to preserve my privacy. Number one. I don't want a central entity. Number two. I don't want to trust anyone. Number three. So I want to replicate bank by using a digital currency, and I want it to be the same as I already had in my cash. So what I wanted in my cash was that my privacy was preserved. As long as I was spending on someone, the bank did not know how much I was spending on whom. So I want the same thing to happen in the digital domain. So is that a great thing? Am I wanting? My wish is to do whatever we were already doing, having exchange of money while preserving my privacy and while not trusting any central entity. However, why do I wish to do it in the digital domain? Because I don't want to physically go and give money. Because I want to do and buy on the net. I want to buy from Amazon. I want to buy from Swiggy. I want to buy from anywhere. Without breaching my privacy, I should be in a position to do that. And I don't want a bank also, because the bank is going to know. So I don't want a centralized entity. I don't want to trust a centralized entity and still work in a truly distributed manner. So what I want is an electronic payment system which does not rely on trust. I don't want to trust anyone, because if I trust, sometimes somebody is going to cheat me. So I want to rely on cryptography instead of trust. So what is my wish? What is my grand wish? My grand wish is to have distributed digital money in a trustless world. I don't want to trust anyone, and I don't want to reveal my privacy. I don't want to tell who I am and still get the services that I want. Now this is about money. Limited to digital money, but since this was proposed first for digital money, so we took the example of digital money. So what do I want? I want to eliminate the central trusted entity, which is the bank. And that is what is meant by that. What does the bank do? The bank keeps a ledger or a database of how much I have, how much I withdraw, how much I deposit. I want to replace the bank. I don't want the bank. I want a distributed database, which is called the ledger. And the data which the bank keeps, how much money do I have, how much I can have spent, how much I have deposited, should also be distributed. And moreover, in a distributed digital currency, I can just spend it twice. In a bank, everything is sequential. You cannot copy a hard cash, physical cash, but digital money can always be copied and replicated. So this is a problem. The second one is fundamental and limited to the currency, which may not be there in other applications. But the fact is, I don't want a trusted, centralized entity who maintains the database, number one. Number two, I want to do all this without compromising my privacy. So, what do I want? I want to go in a distributed setting without sacrificing my privacy. Without has to agree and has to reach to a mutual agreement, and everybody should have the same state of the database. So if I have 100% in a distributed manner, everybody should know that there are 100%. How much it has transferred, how much it has kept, how much he has without knowing who he is. But now, reaching to a consensus, reaching to a consistent state is an NP hard problem. And we know that this is agreeing on something in a distributed, non-cooperative, trustless environment is NP hard. It was also known as Byzantine generals problem. And we need to solve this to be able to reach to an agreement. But let's see how we really go about doing it and solving these problems. So what is my wish? I wish to work in a distributed state identity, and also the transaction, how much I have transacted in terms of services, money, or anything else, not just money, should not be known to anybody else. And the receiver. So in case of money, there'll be spending and there'll be gain and there'll be loss. There can be many applications which does not involve money, but requires consistent state of the database. So let's see, what do we have in store here? So the solution that was proposed which we don't want here. But we want to have the same database which is there, should be maintained. What does the database in the bank? It contains how much money we have, how much is input, how much is output. That is, the database should be consistent. And this has to be done in a distributed manner without having the bank. This is the key challenge. And everybody should reach to a mutual agreement that, okay, this is the state of the database. That means nobody can cheat. But as I told you before, there is no trust. So what is the solution? Where is the bank? So blockchain said everybody is a bank. When everybody is a bank, then everybody keeps a record of whatever is happening. So everybody has a copy of the bank, and that is the distributed ledger which reflects all transactions and ownerships. How much money is being spent, or how much is the outflow, inflow of cash, or whatever application you are doing. And the blockchain takes the role of the distributed ledger. Since the ledger or the bank, if you look at the bank record, it's huge. So yeah, you somehow don't keep the amount of money, but you keep a very shortened version of that, and that's the blockchain. You keep a record of how much somebody has, there is how much is being spent, how much is being debited, how much is being credited. That role of the distributed ledger is kept by the blockchain. So blockchain is the distributed ledger. Where it is stored on all. Everybody stores a copy. And the problem here is that this copy, everybody should have the same copy. They should agree that this copy is the correct copy. Nobody has a wrong copy. So one slide on this. Obviously, the figure of Bitcoin that you are seeing is just hypothetical because it's a digital currency. Let's see what is the role of cryptography in this. So first, to hide the privacy of, to preserve the privacy of the persons, we use pseudonym, which is generated using a public key. For spending a money, saying that I want to send some service, or I want to send some money, or I want to transfer something over the net, I use a digital signature system. So that tomorrow I cannot deny that I have sent. I cannot deny that I have sent. And the other person knows that it's coming from the correct source. The one-way hash function is used for maintaining the blockchain, as we shall see. And for preserving the privacy, I hide behind my public key. Nobody knows who I am. Nobody knows that I am Shekhar Verma. I have a public key, and that public key does not reveal my identity. As you can see, this is the public key that you can see here. Huge public key. So from this, you do not know who I am. But then, as I told you, blockchains are not limited to Bitcoin or digital currency. It has different, extraordinarily different applications. And what powers the blockchain, or what is blockchain in the first place? Blockchain is actually a distributed ledger. What is the problem in maintaining that ledger? Is that I don't agree, and I'm not cooperative. I don't believe in anyone. I don't trust anyone. still I want to reach to a mutual agreement, which is called consensus, without cooperation. I want my privacy. I want my transaction privacy. I don't want the transaction to be linked to me, that I have made the transaction. So I want unlinkability. I want to protect my members. I want, there are two different distributed ledgers. Say one is say Ethereum, another is for example Hyperledger. I want them to talk to each other without knowing who is on which blockchain. For that, I have different cryptographic techniques. So I'm going to talk about the cryptographic tools that power the blockchain or that make the blockchain possible. So I assume that you already know what is a blockchain, but still, let's see what is a blockchain in a moment. So from data management perspective, a database person will see, okay, a blockchain is a distributed database. And it contains a log of all the transactions and organizes them in a hierarchical manner. From a security perspective, why are we doing evolving a list of transactions? Why are we having a chain of blocks? What is a block? So from a security perspective, we try to answer this. A blockchain is created and maintained using a peer-to-peer network. And the consistency of the distributed ledger is maintained through a consensus protocol. Remember, reaching an agreement or a consensus is an NP-hard problem. And still we want to reach consensus. And it has to be secured through intelligent and decentralized utilization of cryptography. So how do I maintain this distributed ledger? By using some cryptographic tools. And everybody is using cryptography. Everybody is computing. So there is a crowd computing there. So what happens? Blockchain uses cryptographic techniques to ensure the integrity. That means nobody can modify its non-modifiability of the blockchain. And anybody who wishes to modify, everybody comes to know about it, and hence nobody can change the database. So I want to use some cryptographic technique for maintaining the integrity of the distributed ledger, which is called the blockchain. And the blockchain is there in the public domain among all users. They are not ready to cooperate. There's no trust. There's no trust among the members, but we make them reach to a consensus without any doubt. That means they must agree that this is the state of the ledger and everybody has a copy of the ledger. So the first thing that we need to talk about is that the distributed ledger, everybody is a bank, everybody keeps a copy of their ledger. So there are two problems. Number one, how to keep the length or the size of the blockchain or this ledger small. If you look at the bank, it's a huge record keeping, but I cannot keep gigabytes of data on my computer. So I want to have reduced size of the ledger that I keep, number one. Number two, as I've already been telling you, I want to maintain the integrity of the blockchain. Everybody should have the same distributed ledger or the blockchain. Nobody should have a different copy. Nobody can disagree. How do I do it? I use cryptographic hash function. So this is the first application, first cryptographic tool which is used, and it's the most important tool, which is the cryptographic hash function, which is similar to the hash, except that's a stronger hash. So how do I maintain? What is a blockchain? So the blockchain has blocks. What are blocks? Are just hashed values of the transactions and other states. I'm not going to details because you already know this. So the global states are protected by a hash. And we construct a hash tree, which is nothing but a Merkle tree. We already know that. And any state change. Suppose I have a hash block, I've hashed and kept the whole thing in a block, and then when more transactions are done, I create another block. So the tree's leaves contain the states, the internal state contains the. So for example, let's see in Hyperledger version 0.6 and later versions have come, the Merkle tree which is used is a bucket hash tree, in which the states are grouped into a predefined number of buckets. Ethereum, we know, is a Patricia Merkle tree, which is something like a trie which is used in routing also and switches also. So idea is that I maintain. So let's look at how does it look. So it looks something like this. But then let's go and do it one by one. So what is there? There are blocks which contain the hash of whatever transactions have happened, and every block then points to the next block. So suppose there are some transactions, money transactions, some 5-6 people have done. In 5 minutes, I take all the transactions, put them in a particular pre-specified way, hash it, add to my block. Then next set of transactions, I'll hash it, keep it in my block. And this is a chain of blocks, which is known as a blockchain. So what is a blockchain? So blockchain is a way to encapsulate transaction in the form of blocks. Which one block, and how do you create a block? Through a cryptographic hash. So it contains a hash value, and they all point to one another like a linked list, and this is called a blockchain. Each block contains a block header and a representation of the transaction, and all of them are hashed values only. The key property is that the blockchain assumes that anybody can behave in a non-cooperative, in a malicious manner. So now what I am doing and what everybody else is doing, and all the transactions which we find are happening, and since they are broadcast on the P2P network, I hash them, form a chain of blocks. But I can be malicious. I can do some tweaking and say some money has been transferred to me, and then I maintain a block which is different from others. Can I do it? How to stop this is what? How to stop anybody behaving in an arbitrary manner is what is now the second problem. So what is the structure of the blockchain? Everybody knows about this. Each block consists of a hash, the hash of the previous block, a timestamp, and the block fruits. And they are arranged in a chained fashion, chain of hash blocks. That's why the name blockchain. So this is how it is. So there are some transactions has already happened. The next block again is done at timestamp 2. So this is the say block number n, which contains the hash of n minus 1, timestamp, hash. And then the second one is again, it contains a block. Every block is pointing to the previous block. What does it contain? It contains hash values. So this is a little more detailed data structures, as you can see. The hash block is contained, which contains a list of the transaction, some random value, some timestamp, the hash value of the previous one, and this is maintained in a chain. And below every block, we have a Merkle root hash. So why do we use a cryptographic hash function? So a hash function, we know, it takes an input of an arbitrary size and produces an output of fixed size. What are the properties? It is collision resistance. That means you cannot take two inputs and create the same output. So if you tweak it, it will create entirely different values. If I give you a hash of a value, say h of s, where s is the input, then knowing S from H is difficult. So it has a pre-image resistance. Similarly, it also has a second pre-image resistance. Why do we use them? I'll be talking about and looking at the hash function in a little more detail soon. But then, why do we use, what are the usage of these hash functions in blockchain? It is used for reaching consensus, which is known as solving cryptographic puzzles. It is used for a generation of addresses from public and private keys so that the privacy is preserved. It is used for creating shortened fixed size versions from all inputs so that the size of the total block is small, which can be done by shortening the size of the public key. If you hash a public key, it will create a small output value. Similarly, I take signatures, I create a hash value of the signature so that the integrity is maintained. So integrity or non-modifiability as a requirement is achieved from a hash function, which is a one-way function. What is the cryptographic hash function used in blockchain? Usually SHA-2 is used, and the variant SHA-256, which has a constant output value. Give any size input, it will create an output of 250. Hash function which is 30, very popular because it's not very good. Then, how do we use it? So in cryptographic hash functions, what we do is for example, the whole thing which is used, the type of SHA which is used in Bitcoin, for example, I take a message and then hash it and hash it twice. So there can be multiple applications of the hash. Why? Because we want to create a Merkle tree. So I do a multiple number of hashes in the form of a mode. So the same hash is also used for mining purpose and consensus purpose. So we'll see in a minute as to why consensus is important and why do we wish to use cryptography for reaching consensus. So let's see. What are we doing? What is the ledger? The ledger is the same ledger which is maintained by the bank. Now everybody has a copy of the ledger, but they do not keep the entire ledger. Everybody keeps only the hash value or the block of the transactions which are happening, and this is recorded forever. But since this is very small, because as you have seen that if you give any sized input, it gives you an output of just 256 bytes. So I want now everybody is able to hash. Everybody knows the process to create a block, but we want everybody to have the same ledger. If everybody has different databases, there's no point working. So everybody must have the same ledger. So how do we agree? If everybody is honest, everybody agrees. But it is quite possible that some people may be malicious. But I want everybody to reach to a mutual consensus or agreement. I cannot use democracy because in democracy, if more than 50% of the people, they tend to be malicious, they can take away all my money. So if there are 10 people and I have invested, say 1,000 in Bitcoin or cryptocurrency, 6 people can gather together and say, "Aapke paas to koi paisa nahi hai, you don't have anything." So then say in my ledger, all money is gone. But I want that the consensus or the mutual agreement that this is the transaction which has been done or had been done before, because everything is recorded, must be on mutual agreement. The nodes do not trust each other. They can make a cartel and fool you and me. So I want the consensus protocol to be trustless. However, we know that reaching to a trust value, reaching to a common trust, as I told you right in the beginning, reaching to a trust value is an NP hard problem. But then people observe that no, reaching to a consensus is a problem only when we are in a deterministic world. If you are in a random world, then the problem gets solved. You can reach to a consensus in a random world, and this is what we use, and one of the methods for doing it is proof of work, wherein we reach to a consensus in a trustless world. What is consensus here? What is the consensus mechanism here? What is it doing? It is replacing trust. You don't agree, we are forced to agree. That means it's easy to prove that what I'm saying is correct, but it's difficult to fake. If I say something incorrect, everybody will know that what I'm saying is incorrect. So this consensus mechanism, friends, in Bitcoin, it was proof of work. In IOTA, as I told you, a directed acyclic graph. Initially, it was curl. Then we have proof of stake in Ethereum. We have end-to-end in Corda. We have bespoke in Sawtooth. We have different ways of reaching to a consensus, and depending on the type of blockchain, the computational power that you have, we can go in for different consensus techniques. I'll just show you, because for example, we have proof of work, proof of stake, proof of burn, proof of activity, proof of authority, proof of time lapse, proof of luck, proof of burn, proof of space, proof of elapsed time, so on, many. And as you can see, all of them are randomized way of reaching to a consensus. The randomized, it's not deterministic, it's randomized. And that is why we circuit through the NP hard problem of reaching to a mutual consensus in a non-cooperative distributed environment. We all resort to a randomized fashion, and cryptography helps here. So what do we want? We want to have a mechanism, and the mechanism is a consensus mechanism, which is a key component. And why do we want to do this? Because we want all the copies of the ledger to be the same. So that means we wish to synchronize or update, and we must reach to an agreement among all parties. In spite of they not agreeing, in spite of people making cartels, in spite of people colluding together and trying to cheat, even if 99% people are against me and cheating, they will not be able to force me to agree, and I'll force them to agree by using this mechanism. What do I say? What do I do? I resort to a hash function. Let's see, and we have already seen a hash function. For example, this SHA-256 is a hash function which was adapted by blockchain, especially in Bitcoin. So let's see, I have a quick brown fox did some crypto. When we do SHA-256, we get this output. 41031239583429, so on and so forth, 256 bits. I just change the small f ASCII value with a capital F ASCII value, and I do the same thing and I get an entirely different value. So the advantage is that if you tweak the input slightly, the output changes directly, and it has pre-image resistance. Given this output, you cannot predict the input. So for example, what is being used right here, I'm showing you what is being used. I give you something, I give you a task. Find out a hash with n zeros at the beginning so that you are able to get a particular hash value. So what I'm saying is, I want you to search in a brute force manner that I'll give you some value. I want you to find out a hash with n zeros at the start of the input. So, for example, if there are no values, I can do it in 10 to the power minus 5 seconds. But if I want you to have some hash value which has 8 zeros at the beginning, then it takes 4, 6, 8, 6 seconds. See, 60 seconds is 1 minute, 3600 is 1 hour. So you will take hours to just find out a hash values with n zeros. So if I take and this is the value that random value which I'll add, which will give you the leading hash values, leading zeros. So I give you a problem, find out, I'll give you a random value together with the I want you to find out the input to the hash function such that it has 8 zeros, or it has 9 zeros in the beginning, it has 10 zeros in the beginning. So we know that calculating the inverse of hash does not have any algorithm. It is an NP-hard problem. So you have to try out every time you have to try out. Once you start trying out, it requires, for n zeros, you have to take 2 to the power n computations. And when you start doing 10 to the power n computations, though somebody who has the maximum amount of computation will win. And this is a proof of work. Why? Because you are trying to compute an input from an output. So the addition of new transactions is performed by reaching to a consensus. And how do we reach a consensus? We say how many and very easy. As soon as we solve this particular puzzle, we know the value of the nonce which is added, and anybody who is able to solve it will be the person, in spite of everybody to my disagreement. If I have solved the puzzle and then I broadcast that this is the puzzle I have solved, I get the right to verify, update and verify the blockchain. So this process of winning the proof of work contest puzzle, solving it, creating a new block is what, and attaching it is what is known as mining. And the participants who solves the puzzle first is the miner of that particular block. So let's have a look, let's revise it once again. What is the miner doing? The miner has to find a random number n once to create the nonce, to create the next block. So what does the puzzle look like? To find a hash with 8 leading zeros. So this is a tough cryptographic puzzle. For example, in SHA-256D, which is used in Bitcoin, if you want to have the target value is T, and then if the target value you just half, then you hash it 256 times. But if you want to have 16 such probability of minus 64, and hence the total amount of effort that you need to do, because you don't have any method, no algorithm exists. You have to put values and check, put values and check, put values and check, and hence it's a brute force technique. So if I have more computation power, that means if I work more, I'll be able to win the puzzle, I'll be able to solve the puzzle. So this is proof of work, that I worked hard for the proof. And if I win, then it's very easy, because I give you the random number, you can easily verify. Forward hash is very, very fast. So anybody can verify. So I become the miner and I'm able to mine. So what is the protocol here? The protocol is very simple. Suppose an email client wants to send an email to the email server. The client and server both agree on a cryptographic function H, which maps input string to an n-length output string. However, the email server sends a challenge string C. What do? I have to attach another string X, which was a nonce there, so that the hash value contains k zeros. So now, since I cannot really predict what will be, the inverse prediction is not there, so I cannot take a number with k leading zeros and do inverse hash. I have to keep on using random values of this X and concatenate with C, keep on hashing it, and this will take a lot of time depending on how many zeros I want. So since H is a pseudo-random function, H is a hash function, the probability of success is just 1 upon 2 to the power k. So I said you require 2 to the power k computations to know this particular X. And this process, as I told you, is called mining. It's difficult to do, very easy to verify. I just take this H concatenated with X, just hash it fast. It is very, very fast. We know hashing is very fast, and you will know if the result is correct. So this is how we reach to a consensus. This is how we reach to a consensus in a distributed, trustless, non-cooperative requirement. And this is one of the biggest additions which is there for maintaining and the integrity of a distributed ledger, which is called the blockchain here. Then, suppose you have a wireless sensor network, or suppose you have a P2P network, or suppose you have an Internet of Things which is connected to the internet. Now what happens is, suppose I have a blockchain which is a big oil infrastructure or financial blockchain, and it is over a P2P network. Then I want everybody to be synchronized. Everybody should be synchronized. Everybody should have the same ledger. But there is a propagation delay, as you can see. And this propagation delay, suppose there is a 1 second delay, then the transactions which I am processing, the transactions or you are processing, will lead to a non-consistent state of the ledger. And this can constitute an attack. The first attack was the net split attack, in which an adversary says all connections are through me. It's like a black hole or gray hole attack. So me as a node, I start routing my traffic through that particular router, and he blocks my traffic, so nobody knows. I cannot participate in the consensus process. And this causes inconsistency in the network. This is a routing attack. So a set of participants can be isolated from the network by introducing artificial delay at some router. This is a routing attack. Then there can obviously be, if you can do routing attack, you can do black hole attack, you can do a denial of service which is distributed. So this is an active area of research which has not been solved yet. So I'm not offering any solutions here. But we need to do a lot of research. If you have a network which is open to the public and is open to attack, it has a large propagation delay, then these attacks are possible. So let's see, look at the blockchain. So now, as you can see, we have different kinds of blockchain. We have permissionless public blockchain, we have permissioned public blockchain, we have permissionless private blockchain, we have permissioned blockchain. And I'm not defining it, my friends, because Dr. Venkateshan, who's going to be the next speaker, will be talking about these things in quite some detail. The application domains, for example, we have a permissionless public blockchain. The decentralized P2P network, the application is distributed, the anonymity is high, the scalability is not there, the challenges are privacy, scalability. For example, a permissionless public blockchain was Bitcoin. Any cryptocurrency most of the time is a permissionless public blockchain. A permissioned private blockchain, the advantage is that everybody is cooperating. So the reaching to a consensus is cooperative. You don't have to fight. You may be allowed to really update the blockchain. So in a permissioned private blockchain, consensus mechanism is not really a big challenge. It's centralized. And the example is a Hyperledger Fabric, and Dr. Venkatesan, as again I told you, is going to talk about that. So let's move and see what are the other security challenges and what type of cryptography is used in blockchain. First, for this, we look at the layered architecture of a blockchain. So we have different layers. We have smart contract layer, we have transaction layer, we have consensus layer, we have network layer, and the database layer. So database is the distributed ledger. The network is the network layer which we are talking about, in which we have a problem of different kinds of network attacks. The consensus layer, as we have already seen, works on proof of work, proof of stake, proof of burn, proof of elapsed time, and other some cooperative consensus mechanism, for example, in Hyperledger. When what is transaction? Transaction is the money I transfer. The service that I receive is a transaction that I am doing. For example, I pay so many rupees to Amazon, transfer money to get something. And a smart contract, what is a smart contract? This is interesting. Smart contract is the way in which you transact. So whatever who will pay first, how much will be paid, what will be the manner, and the whole thing will go around that. This contract is written in the form of a program. So this is a rule-based program. So this is a program. The important thing is that nobody should be in a position to tamper with this. For example, we have Solidify in Ethereum, and the important thing is that it should be stateless. It should be a Turing incomplete or a Turing incomplete language. More of this by Dr. Venkatesan. But then the challenges everywhere, as you can see, are anonymity and privacy. And then we see what cryptographic techniques we are going to use for achieving anonymity and privacy. So the smart contract layer processes contract data and results therein. The transaction layer creates transactions or whatever being transacted or exchanged, the money, the services. The consensus layer we have already seen, which allows us to reach to a mutual consensus and update and maintain and verify the blockchain and increase the blockchain. The network layer we know in IoT environment, in P2P environment, over the net. So that's a network layer, and we have already seen some attacks on it. And the data that we maintain, that's the database. Now, the major problem which we have is that I want to preserve my privacy, and I want to preserve the privacy of my transactions. Let me look at what I mean to say. So I don't want anybody to know how much money I have transmitted. The sender knows, the receiver knows. Nobody else should know. Nobody else should know who is the transmitter, who is the receiver of funds, how much money has been transferred. However, they should be in a position to verify that the money transfer has been correct. That means the ledger maintenance is correct. It's not that the transmitter has transmitted or sender has sent money, the same money twice, because one I sent to person B, another to person C. So I want to maintain the integrity of the ledger. I want to reach to a consensus. I want to be able to verify that the transaction is correct without knowing who has transferred to whom and how much has been the transaction. So let's see how this impossible thing happens. So what I want untraceability. For each coming transaction, I don't want anybody to know who is the sender or who is the receiver. Unlinkability. For any two outgoing transactions, we should not know whether it's going to the same person. So I should not know who is the transmission. transmitter that I don't want, I want untraceability. Nobody should be able to trace the sender. Nobody should be able to link a transaction with a receiver. So I want complete anonymity. Sender is not known, receiver is not known, how much money is going is not known, from whom it is going it is not known, to whom it is going it is not linked. I don't want, for example, Alice and Bob, they send to Trent. And I know who is presenting to whom, because I am creating the block here. But if I want transaction A and sender is not known, transaction sender 2 is not known to the general public, then it's a case of unlinkability. Similarly, if Alice sends to Bob A and Bob sends to Trent and Trent sends to Alice, so nobody will know. If Trent does not tell you, nobody will know. So how am I doing? Here nobody is able to link, here nobody is able to trace. What is untraceability? The senders are not known. What is unlinkability? The receivers are not known. So unlinkability, receivers are not known, who is going where, and untraceability, this fellow Alice thinks it is coming from Trent. He does not know who is behind Trent. So this we wish to replicate in the blockchain environment. So what people started doing was started making plugins for this security. So one such plugin, one such tool is Monero, which is specific to Ethereum, Monero generates public key and private key using elliptic curve cryptography. And for untraceability, it uses ring signatures. We'll see in a moment what is a ring signature, but it uses ring signature. So what happens in a ring signature is that I sign using my private key with public key of my neighbors, and nobody can know if I have used some 6 public keys. The person, anybody who is observing that particular ring signature on a message will be able to verify that yes, this is a legitimate signature, but will not be able to whom of all these 6 have signed. So this is a ring signature. Similarly, for unlinkability, I use what is known as a stealth address, which is address which we generate and nobody can trace this particular address. So I use a digital signature. For example, I use ring signature, but let's see what is a signature. So in a signature, what we do is I use public key cryptography. And what I do is I encrypt a message. I take a message, do the hash of it, I encrypt it using a private key. So anybody can easily then verify it. By how? By decrypting it, it will know what is the hash value. I sent the message, so the hash is a well-known function. So hash is also given, the hash is, you hash it, so you get the correct output. That means, again, I repeat, I take a message, hash it, encrypt it and send. So the message and the encrypted value of the hash is sent. Now that the receiver who wants to verify will use the public key of the signer to decrypt and then use the hash function which is publicly available, it's known to them, to take the message and hash it. The message and the encrypted hash is sent. Encrypted hash, this is what is known as a digital signature. So this can be used to guard against tampering and forgery. And signer cannot say that I have not signed because he is using his public key to sign. So there is a non-repudiation also, which means that I cannot deny tomorrow that I have made this transaction. So in a blockchain, this is the signature scheme is used to sign that transaction, and hence it authenticates the sender because only the sender can sign. The verification can be done by public key. The signing is by the private key. Since it's actually encrypting the hash value of something, hence the transaction integrity is also maintained. If I sign using my private key, I cannot tomorrow deny that I have signed it. So I've seen it. So that's non-repudiation for you. So signature scheme is used in every blockchain for privacy, anonymity, and unlinkability. Because nobody knows who I am. I'm hiding behind my public key. And I'm signing, so everybody knows that some legitimate person has signed. And since I'm encrypting the hash value, the transaction integrity is maintained. Since nobody else can create a signature without having a private key, I cannot deny tomorrow that I have seen it. So that's non-repudiation. So I'm able to achieve privacy, anonymity, and unlinkability. How do I do it? So there's a signer, there's a transaction block. I sign it, I hash it, the hash value is same. A transaction is there, I encrypt the transaction, and then I create, by encrypting the hash value, I create with the signer's private key, I'm able to create a digital signature. The verifier takes the transaction value, knows the hash value in the public domain, it's not private, so I hash it. The signature I take, I decrypt it, I get the hash value, so I match it. And this requires not the private key of the signer, but the verification is fast, requires only the public key of the signer. So there are different types of signature schemes which are used. For example, there's a group signature. And in a blockchain network, when a transaction requires a signature from a group of participants, it's multi-signature is used. And it is used in open chain, multi-chain blockchain platforms. And when multiple people need to sign to create a valid signature, then the risk of theft is lessened and mitigated. Then I use a blind signature. What is a blind signature is very interesting. I put my signature, but I do not know the content. So I am, for example, how is this possible? So I'm given the message, I'm given its hash. I know that I cannot create the message for the hash. From the hash, I cannot create the message, but I get the hash value. So I know if I am signing the hash value, means that I am signing the message. Suppose I am given a message, instead of the message, I am given the hash value. So I sign the hash value. So suppose in a paper signature, in a physical signature, nobody shows me the message. Any message is not shown to you. I'll give you only the hash of the message. I put my sign on the hash of the message. Nobody, I have not seen the message, but this hash is, as soon as the hash is verified by my signature, then nobody can create another hash, pre-hash, and any message cannot be created, because inverse of hash is difficult because it has pre-image resistance. So that's a blind signature. So anybody who's transacting, who's signing, does not know the money, because the money, for example, I have to transmit 1 lakh rupees. I take that 1 lakh rupees, I add a random number to it, hash it, and then give it to the person by signing the hash value. So nobody knows how much I am transacting, but everybody knows that I am transacting something correctly. The receiver gets the money, hashes it, decrypts the hash, verifies the signature, so it knows that I am getting the correct information. So everybody knows that the transaction is correct, but nobody knows what is the amount of transaction, and hence it provides the unlinkability and anonymity of the transaction. Unlinkability, why? Because it does not know the receiver. And why anonymity? Because you do not know the money, you know only the hash value. So a blind signature can be used to provide anonymity and unlinkability to the transacting party and the signer. This is used in blind coin, and it's used to provide unlinkability of the transactions. And in Bitcoin also, people are trying to use it for anonymity. But then I can use a threshold signature. So if multiple people are required to sign, then A signature will be created only when a threshold T of the end party is signed. And this again is used for providing anonymity in a blockchain. Most importantly, I've already told you that ring signature is used to provide anonymity, and the privacy of the person who is making a transaction is preserved. So what do? In a ring signature, I told you I sign with my private key, but I make a ring by using the public key of others. Where do I get the others in a blockchain? Those who have already made transactions. I take their public keys, use their public keys and my private key to sign. Signing, once I sign, then anybody can verify this, but will not be able to know whose private key has been used. So the verification requires only the public key of the people in the ring. So if I use some 5 public keys, it will know that one of these 5 we have signed, but who has signed is not known. So this is used by Monero to create untraceable payments. And it is also used by Ethereum, it's used by others. And what is used is a ring signature and a linkable ring signature is used. And I'm not going to details of that, but it will take a lot of time. Perhaps it will take an hour by itself. And a linkable ring signature is used. Why? Because if I make the same transaction before, I transact the same money again, then it gets linked to me. Then I want to prove that I have transacted without showing you the proof. So I want to convince everyone present, all members of the blockchain, that a valid transaction has been made. I want to prove. However, I don't want to give and show that I have transacted so much of money to so many people. So one way was the ring signature. The other way, which is more popular now and it's used in Algorand and other blockchains, is what is known as a zero knowledge proof. So what happens in a zero knowledge proof, which is again a cryptographic method and a cryptographic protocol. So to achieve anonymity and to prove something without revealing any other information except the statement. So let's have some basics, because again, as I told you, we cannot go into details, but we have 2 parties, a prover and a verifier. The prover asserts some statement. For example, it says that the 3 angles of a triangle sum to 180 degrees. Without showing the proof, which we learnt in class 8, I want to prove to the other person that what I know the proof. Suppose I have a red ball. Without showing the proof, without showing the red ball, I want to convince the other person that I have a red ball. This is what is a zero knowledge proof. The prover asserts some statement. For example, the transfer of an asset is valid without showing anything about the asset. If I transfer 10 rupees, I say I have transferred rupees without telling and without showing the transaction proof. So if I am able to do that, then I have a zero knowledge. This provides confidentiality of an asset. We know, friends, that this is a huge protocol. This is a very heavyweight protocol. So what I want is a lightweight zero knowledge proof. And this, as I told you, is used by a blockchain platform called a ZeroCoin. ZeroCoin uses zero knowledge proofs for untraceability and unlinkability. And one of the platform is Zcash also. So ZeroCoin is a decentralized mix and extension to Bitcoin. So this is a plugin for Bitcoin. In another protocol, for example, a Zcash protocol, that's a standalone protocol or standalone blockchain network for transferring assets while maintaining the untraceability and unlinkability of the transactions. So how do I do it? What version I want. So example, in Zerocoin, which is an example, and as I told you, it's not necessary that we use it only for digital currency. I'm just using this example. I want to produce a secure commitment and record it in the blockchain. And when I record it in the blockchain, then I convince others that I have made a transaction, a valid transaction, without showing the transaction. And this requires a zero knowledge proof. However, the existing zero knowledge proof that we have is very costly, is very high, has huge complexity and a very large proof size. It's interactive. I want a non-interactive proof. So in Algorand or Zcash, what was proposed was a zero knowledge, succinct, non-interactive argument of knowledge. It's a zero knowledge, that means it does not reveal anything except the proof that I have the validity of the transaction. It's succinct, that means it's very short proof, very fast, quickly you can verify. It's non-interactive, there is no multiple message exchange. I just say, give my statement, and I don't have to give anything else. No other proof is required. It's automatically verified without revealing anything. So this is what is known as SNARK, ZK SNARK. So what do I do there? I use an arithmetic circuit, and I'll show you a short proof so that you have an idea of what is happening actually. What is happening here? So just a peek into what is happening. So allow me. So what is ZK SNARK? It's a zero knowledge, succinct, not interactive argument of knowledge. So what is non-interactive? Non-interactive zero knowledge proof is a variant of zero knowledge proof in which there is no message exchange between the prover and the verifier. Just one broadcast by the prover. What it uses are some common parameters. A common reference string shared between the prover and verifier is enough for the proof. There is no other interaction which is required. What is succinct? It can be verified very, very quickly. So no heavyweight computation is required. So let's see what is there. So the zero knowledge proof, the client or the verifier learns nothing but the validity of the computation. Succinct, the proof is tiny as compared to the computation. I'll not go into details of this. It's non-interactive. It has arguments. The arguments, the soundness, that means if I can prove, I'll prove it. So what is the proof now? Let's understand and see the proof. And what is ZK SNARK? So first, both parties have access to a string of random data. And this particular random data is created using some secure multi-party protocol, which we'll see in a moment. The prover simulates the verifier by selecting the data from the common reference string. Then what happens is, let me see friends, I think what I'm being told is that I'm getting disconnected, so let me that's a common string that you have. So very easy. Hello, am I audible, sir, or not?
Yes, sir, audible.
Okay, sir.
Please
I got
continue.
a message from the organizer that there's some problem. I think that problem solved itself. So I'll continue.
Yes,
Okay.
yes, sir. Please continue.
Okay. Thank you. Nice solved. Thank you. So let me tell you what is ZK SNARK. The main idea, very easy. You have two polynomials. You have to just multiply Px with Qx is equal to Sx with Rx. But I don't want to tell you what is Px, what is Qx, what is Sx, what is Rx. So I resort to what is known as homomorphic encryption, in which I can do multiplication of the encrypted value of Px with the encrypted value of Qx and I'll get a value, and I'll get the product of PX and QX in the encrypted domain. That means if I take the encryption of 2, I take the encryption of 3 and multiply them, I'll get the encryption of 6. This is homomorphic encryption. So what I do is I encode a polynomial, and then the program is to be checked, is compiled into a quadratic equation, and the polynomials are Tx, Hx, and Ws and Wx and Vx, and whose equality are checked. So let me come to a very so what I do is I just encrypt the values of Tx, Hx, Wx, and Vx and keep it. And then what I do is my value is actually x naught. My value is x naught. So I give the encrypted value of px naught, encrypted value of qx naught. So people, what they do is just multiply these two. They know the product already because they knew px into qx naught, so they can easily verify. So what I'm doing is the verifier chooses a secret evaluation point x s to reduce the problem. So when you are trying to multiply two polynomials which are coming from the transactions, at some value of the polynomial, any random value, any value it takes, the verifier takes, calculates, it knows the encryption value there, and then multiplies and checks, okay, is it coming to the value I want? So it will take the encrypted value of px, takes the encrypted value of qx at point x naught. It knows the value of the product, the encrypted value of the product, just multiplies it and checks it. So without knowing what is a transaction, without knowing x naught, without knowing the value at s, it just verifies, and verifies very quickly. I know it, what I'm telling is a little abstruse and not really into it, but the idea is that I am able to verify. For example, I'll give you another example. For example, I wish to search something on the cloud. I've kept some data in encrypted domain. So I send the keyword in encrypted domain. So the cloud does not know what is the keyword. It is able to do matching in the encrypted domain, and hence will know whether this document has this keyword or not, without knowing what is the document, without knowing what is the keyword. That's the idea of homomorphic encryption. And here, that is used to do some arithmetic operation like multiplication, and it is just doing simple multiplication but in the encrypted domain, and the equality tells you whether the transaction is correct. So homomorphic encryption is used to evaluate the polynomial at x naught. So encrypted value of px naught into the encrypted value of qx naught is checked, and similarly two other values are checked. So it knows, okay, without knowing, this allows the prover to compute the encrypted value at t of s. So any random value is given by the verifier s. So the prover computes the encrypted value of ts, encrypted value of hs, encrypted value of ws, encrypted value of vs, sends it, and it does not know s also, and it knows only e of s, and multiplies to check. The verifier can multiply and check. And again, I'll not go into details of this, but it is still made more difficult by adding some random values. So what do we use here? We used zero knowledge proof. Specifically, we used ZK snark for maintaining the anonymity and the unlinkability. What are the encryption schemes that we used? The first, we use symmetric encryption in a smart contract. This is a smart contract is nothing but a program. How does the transaction take place? That is a program which is known as a smart contract. And I told you the property is that it should be Turing complete. And Hyperledger uses that, symmetric encryption. In Monero, we have range proofs as to what is the actual money transferred, which we are showing, which uses homomorphic encryption, which is another cryptographic principle. Finally, suppose two different blockchains need to talk. I want, for example, I want one blockchain to talk to the other blockchain and jointly compute some value. Most popular example which is given is I want to calculate among 10 people who gets the maximum salary without knowing the salary. So this is what is known as secure multi-party computation. So for example, Enigma, which is a blockchain network, uses, for very strong privacy, uses secure multi-party computation for transferring data. And why? Because every party has small amount of random piece of data. Nobody has the entire data, and that is used by Enigma. And how does that computation take place? The computation, example, I wish to add x1, x2, x3, x4 without knowing x1, x2 or x3 or x4. And suppose my contribution is x5, I add all of them without knowing the individual values. This is done using homomorphic encryption and secure multi-party computation, friends. Hawk, they transfer, they have a privacy preserving smart contract, uses again secure multi-party computation. Why? Because the generation of common reference point requires, I have to pass the entire common reference point. I don't want to do that. So everybody has a random part and I transfer that using secure multi-party computation. So any computation, nobody even knows what is a common reference string which was there in this NAR. Again, for example, in VanChain, this is a blockchain framework used in business. It wants to transfer an asset to another blockchain, for example, an Ethereum blockchain, and does not want to tell what is the asset value. For example, I want to transfer an asset ETH. So this is an Ethereum blockchain, and I want to transfer this value, asset value, and do some calculation without telling what is being transferred to the other blockchain. From Ethereum blockchain, I wish to transfer something and do some calculation of the ETH. So this can be done, my friends, using the secure multi-party computation. How does it do it? First, the amount is locked, which is using some smart contract. This locked amount holds the control of funds. When it is transferred using some calculation here, which is done by these storeman nodes, which are special nodes doing multi-party computation, then the locked amount is released. And once it is released, the equivalent amount is burnt off. So nobody knows what is the amount. You do the calculation using the secure multi-party computations in which multiple storeman nodes are there. Even they do not know what is the original value, and they do the calculation, transfer the output, which is a calculation, and then burn up the value. So these storeman nodes use public key and private keys of the related locked account, and then the private key is actually scattered among all storeman nodes. So nobody can know what is the total private key, and the private key is generated using multi-party computation using secret sharing. Okay, this is the mechanism which is used for transferring. So the storeman nodes do not know the private key; they just have fragments of private key, and by using these fragments itself, they do the encryption here and the decryption, then decryption. So finally, one last cryptographic tool I just wanted to show you is that I want to transfer some money. I'll give you an example so that you are able to understand. I want to go to the party. I want to go to a movie. My friend wants to go to in a restaurant. We are over the phone. We have to decide who wins. So what I do is I say, we both toss a coin. We both toss a coin, and if both of them get heads or both of them get tails, then we go to the hotel and eat. If I get a head, you get a tail, or if you get a head and I get a tail, that means what we get are different, then we go to the movie. The problem is we are not together. We are at two ends of a mobile phone. We are distributed. So if I toss a head and I get a head, I toss a coin, he will say, no, I've not got a head, I've got a tail. If I say I've got a tail, he'll say I've got a head. So how do we solve this problem? So what I do is I have a commitment scheme. What I do is I generate a random number and if I get a head, I put H somewhere in the middle, hash it and send it to him. So I'm not sending that I've got a head or a tail. I have just got a random number, say two random numbers. I just send the complete random number to him and put my H somewhere in the middle. And I have hashed it. Now what happens? He tosses the coin and gets a tail. Then he tells me that I have got a tail. But now when I say that I have got a head, he knows the random number. He knows where to, and also tell him where to put my H. So he asked me to put my H at the right place, hashes it. Since I cannot create a pre-hashed function, so I cannot really do anything wrong. Because once I have made a commitment, I have given a hash function, I cannot cheat. So this is what is known as commitment. Commitment is something in which I can hide and then bind. I can hide my secret and then bind my secret. That means I cannot change it. That means the first party cannot change it. So this is a two-phase game in which there is a commit and an open. So a commitment scheme satisfies two properties, hiding and binding. Hiding ensures that the receiver cannot see the message because I have made a hash out of it. Binding means that the sender cannot change the message. So a Peterson commitment is used in blockchain. For example, somebody wants to send an amount B. A wishes to send an amount to B, some receiver R. Then it calculates a commitment CB, which is equal to XGH, where X is B is the amount, X is some random number. So B is hidden in this commitment, XG plus BH. And X is the random number. So now the receiver knows what to do. So it is there. Anybody can verify. So the amount is known to the receiver, but nobody. And so what I do is I have a mask function, which is equal to X plus H of R KB1. Amount is equal to B plus H of KB1. So anybody can verify that the amount has been transmitted. But if the amount is encrypted, only the receiver knows what is the amount has been transferred. So this is the Peterson commitment. And how it is used in Zcash or Zerocoin? It hides the serial number and binds it. So the serial number S is, what do? I use a digital technique in which I use a discrete log. So the commitment is equal to G to the power S, H to the power Z, mod of something. So H, G is a generator, H is and P are known to everyone. But knowing G, knowing S, knowing H, and even knowing C, you cannot know what is S. So if you know G, you know H, you know S, you know C, you cannot calculate S. That's the hardness of the discrete log. So the user chooses S, Z and computes and publishes C. Now when it publishes C, it cannot change this. And Z cannot compute C. Anybody who's seeing it cannot compute even if everything is provided. If S is not provided, C is provided, G is provided, H is provided, Z is provided, you cannot calculate S. But you can easily verify. If I give you an S, you can easily verify that this statement is correct. So anybody can then prove that when the serial number S is published, the user can prove the ownership by providing that. So this is a commitment. So this commitment, my friends, is used in Monero for the range proof. I tell you what is the range of my money I'm transmitting. And this is used for confidential transactions in a blockchain. Friends, I have told you so many things about how you initiate and broadcast a transaction and verify it using initial signatures, ring signature, threshold signature, blind signature. How do you check the validity of a transaction? How do you maintain the integrity of the blockchain? By using proof of work, by doing proof of stake, which uses hash, cryptographic hash function. How do you protect the integrity? By hash function. How do you do proof of work? That is done using a cryptographic puzzle based on hash. How do you maintain the privacy, unlinkability, and untraceability of a transaction? By using ring signatures or by using zero knowledge protocols or by using linkable ring signatures. How do you transact between different parties without anybody knowing the private key and by scattering the private key? That's by using a secure. You are able to calculate a value without knowing what are the different inputs to the value. They are encrypted by using homomorphic encryption and secure multi-party computation. My friends, I have not yet told you about protection of members, which uses a verifiable random function. And I have not told you some a little more things which are modern and are being used in blockchain. So for that, probably we'll have some second lecture or a third lecture sometime. But for now, I wish to do some shameless advertisement. We at IIIT Allahabad, we are a group of comprising Dr. Manish Kumar, Dr. KP Singh, Dr. S. Venkatesan, who is going to talk to you after some 15-20 minutes, half an hour, and I am Professor Shekhar Garma. We work on security, we go and work on blockchain, we work on lattice-based cryptography, we work on cloud, we work on IoT security. We also work quite a lot on we have a very strong machine learning team in which we work on secure machine learning, we work on manifold learning, we work on learning on graphs and cutting edge tools we develop. We don't work on applications, we work on machine learning techniques. Come and join us at IIIT Allahabad, friends. Thank you so much. Thank you so much. So if the organizers are ready, I'm ready to take questions.
So yes, it was a very good session. So do we have some questions from the attendees?
So it seems that the attendees were engrossed or they were finding it too difficult.
Earlier it was actually a network issue, but later on it was very smoothly going on.
Yes, sir.
So let's wait for a couple of minutes, sir.
Yes,
if
please,
anyone asks the question.
So I'll share the PPT as requested. It seems that there are no questions.
I guess there are no questions, sir.
So thank you so much. I think
thank you, sir. Thank you very much, sir.
Thank you so much. Thank you so much. Thank you. So thank you so much, and thank you all. Have a very nice day.
We'll be joining within 5 minutes, so please bear with us.